So today we will discuss about this Zariski tangent space at a point uh, in an affine algebraic set. So Zariski tangent space at a point of an affine algebraic set. Okay. So suppose X is a closed subset inside AN. Then X is given by this some v of f1 up to fm, means zero set of some polynomials for some polynomials f1 up to fm inside k x1 up to xn, this polynomial ring in n variables. Now recall the definition of Zariski tangent space. Recall so T P x. So this is defined as the all the points inside an such that this summation del fi del xj, j runs from 1 to n at p times aj, this is equals to 0 for all I equals to 1 to m. So sorry, not this. Okay, we want to show this. Want to show this. Okay. And recall the definition of Zariski tangent space. Zariski tangent space is means for a point inside X, the Zariski tangent space is defined as this Tpx is equals to this dual of this mxp mod mxp square to k, this hom. Now this is a finite dimensional vector space. By using Nakayama's lemma, we can see this mxp mod mxp square, this is finite dimensional k vector space. So we consider its dual. This is the means where this k is the residue field, means oxp mod mxp, and because this is k is algebraically closed, so means this residue field will be equals to k. Okay, because k is algebraically closed. So this was the definition of Zariski tangent space, and we want to show that this Zariski tangent space, this is equals to this collection of all these points such that they satisfy this certain linear equations. Okay, so this is what we want to show. Now so we can write this as proposition. Proposition. Now proof. We have to use some linear algebra, results. So suppose A is this polynomial ring kx1 up to xn, and Ax be uh, this kx1 up to xn modulo I of x, this ideal of x, and P be the point, say the coordinates are alpha 1 up to alpha n inside x, and suppose capital MP be the corresponding, this is inside x and x is inside also an, this is closed. So we are considering this MP the maximum ideal generated by x1 minus alpha 1 up to xn minus alpha n, this is inside A, and we are considering this small mp to be this capital MP modulo I of x, this is inside A of x, this coordinate ring. Okay, so before means proving this means we want to uh, uh, yeah uh, observe something. So uh, for any point, no, for any polynomial f inside kx1 up to xn, we consider this, and for any point inside say an, okay, anyway, so we consider this f of, we already have this p inside x, so we consider this, we define this as a that y, say this is a this is this polynomial, uh, suppose this is y1 up to yn, so this we defined as this summation del fi del xj, sorry, del f del xj evaluated at p times yj, this j runs from 1 to n. So we consider this polynomial, this is and we can think this as a linear functional on this kn, we consider this means for f this is the linear functional on kn. Okay, so this is inside kn star, again dual. So now now from the means suppose means we write it this part, we write something like, we denote something, wait, so let this T to be this set, this all this A1 inside to AN, this is inside AN, such that this F um, Fi P len, this evaluated at this equals to 0 for all I equals to 1 to m. So this was the means our this right hand side of the proposition, right? So we have this. Now let this IP lin, this we denote by the means all those linear functionals such that this f this p lin, where this comes from, this f comes from this I of x. Okay, this, or anyway we don't need I of x, or we can write that where f comes from this ideal generated by this f1 up to fm. Okay, then uh, this is this IP lane. This is a sorry, this is a subspace. This is a subspace in this Kn star subspace. Subspace. It follows from the fact that it is ideal, means we can show, means check. Okay, and the tangent space, not tangent space, the T that we defined, this is actually equals to the annihilator. The annihilator of this means what is the annihilator? Means you need to recall the means linear algebra definition. The annihilator is defined as this, all those v inside say Kn such that this theta evaluated at v, this is equals to 0 for all theta inside this. So this is the annihilator. Annihilator. Now, so we have to show that this Tpx is equals to T, right? Now we consider another thing. We consider this its dual, this T star, this dual of this T. Okay. Now we know that consider this T star, T dual. Now consider this map, this Kn star dual to this T star. So we have a surjective map, right? Surjective linear map, because any linear functional on T, sorry, any linear functional on Kn, if we restrict it to this T, this will give a linear functional on T. Okay, and it is surjective because any linear functional on T, any linear functional on T, because we have this T2 sorry, so this will be a surjective linear map. Why? Mm, so our claim is this row, this is a surjective linear map. This is actually restriction, given by restriction, by restriction, the surjective linear map. Surjective linear map. Why this is a surjective linear map? Okay, you have to means figure out means how means we have to do something here, but this is, you have to also check, because I need to check some details. for that. Okay, so this is a surjective linear map. Now from here we know what is the kernel is. The kernel of this row, this map, this is actually the annihilator of this T, annihilator of this T. It follows from the definition. Just simple, it is restriction. This row is given by this restriction. So kernel will be means, of course, the any means uh, annihilate. Yes, kernel will be means kernel of this morphism of this k-linear map, surjective k-linear map will be given by this annihilator of this T. Right? Fine. Now we know that this T is actually annihilator of this IP lin, its annihilator. Now if we take means annihilator twice, then we will get the original space, means this is a result from linear algebra. So this will give us double means we have to take annihilator twice, then we will get this IP lin. So this is the kernel. So kernel is nothing but this. The kernel of rho, this is IP lin. Okay. Now, so from here, means using this, we can see that this T is actually T dual. This is actually isomorphic to this Kn dual modulo this IP lin. So this is the fact that we have to use. Okay. Now we come back to our means original proof. So we want to show this, right? This mxp mod mxp square, its dual, this is isomorphic to this T, the way we define. Okay. Now and we also have this MP as the maximum ideal generated by xi minus alpha I inside A. Okay. Now we consider this a map say MP to Kn dual. We consider this map, which map means where means some f, it goes to this FP lin, means the way we define, means this is means this is a linear polynomial whose coefficients are some del f del x psi. Okay, evaluated at P. So this is now we can show see that easily, we can see that it is surjective map. Why? You can see that means all these xi minus alpha I, this thing, they will give us a means standard basis, means ith standard basis, say ei or ei star or something we can say. So they will give a standard basis, gives standard basis standard basis of this Kn star. So this is also linear map, of course, K linear map. So this is a surjective k-linear map. Okay, say D. So D is a surjective k-linear map. Surjective k-linear map, and we can see that the kernel of this D, this is actually MP square. This is also easy, check this thing. Okay, so this is, so now we have this MP mod MP square. This is isomorphic to this Kn's dual. Okay, now remember this surjective map means we already discussed this Kn's dual to this T dual, this row, this surjective map. This is a surjective map, and also now we have this surjective map MP to D. We have this surjective map. So this will be a surjective map, and its kernel of this row composition D. This will be kernel of row composition D. This is nothing but this D inverse of, we already know the kernel of row, so this is IP lin. And if you means see the definition of this IP lin, and if you take this means D inverse, that it is easy to see that this is actually equals to I plus MP square. This is again check this thing. Now from here we get this T is not T dual, this is isomorphic to MP mod MP square plus I. Okay, what is I? I'm writing here I, but actually I is this. This is I. Sorry, I didn't mention it. So this is I. Okay. Now, now consider this AX. AX we already know this is A mod I, right? Sorry, not A mod I, but A mod I of X, right? I guess we have to do something here. Let me change something. We change that this Ix to be this ideal generated by this F1 up to Fm. Okay. So using this, I guess so this is actually Ix. And from here, okay, so we take this as Ix, I of X, I of X. Okay, sorry. Now this the corresponding this maximal ideal corresponding to this capital MP, we consider the, suppose this capital MP with the corresponding capital MP bar with the corresponding maximal ideal corresponding a maximal ideal of MP in AX. Okay. Now from there we see that this T star, this is isomorphic to which is isomorphic to MP mod MP square plus IX. Now this will be actually isomorphic to MP bar mod MP bar square, and this is easy to see. Okay. Now from here, now sorry, not this is MP bar, we already defined something here. This is MP, right? MP is the corresponding MP is the corresponding maximum ideal of MP. Maximum ideal is the corresponding maximum ideal, sorry, is the maximum ideal corresponding to, is the maximal ideal in AX corresponding to MP, corresponding to MP, capital MP. So now, so this is actually small MP mod small MP square. Okay. Now, so this is the case. Now I leave this as an exercise, that you have to show that this MXP mod MXP square, this is actually isomorphic to this small MP mod small MP square. So this is an exercise. This is also easy, means you have to just you have to observe these things, that this is, we are considering affine varieties, right? So OXP, this is isomorphic to AX localization at MP, and so MXP will be isomorphic to MP AX MP localization at MP. So using these two facts, use this this fact for showing this thing. So if you are you can show this, then we are done, right? Because this is nothing but our definition TXP star, because double dual we are taking. So sorry, so wait, so TXP star, this is actually equals to MP MXP mod MXP square, and we are showing that this is equals to MP mod MP square, right? Now we already know that this is isomorphic to T, where T is nothing but sorry, T star, where T is nothing but that means how we define this thing. So it will be equals to this TXP or I guess I'm messing with this notations. This is TPX, sorry, yeah. So TPX, this is actually isomorphic to T, means this is isomorphism as k-linear isomorphism, as k-linear isomorphism, and T is actually this set, this A1 up to AN inside AN, or this is actually same as KN, right? So this is where the summation del Fi del Xj, this is equals this evaluated at this point P times Aj, j runs from 1 to n, this is equals to 0 for all I equals to 1 to n, and this was our definition of in other In other words, this is actually Fi lin P. This yeah, evaluated at this a1 up to an, this is equals to 0 by our notation. So we are done. So we had to use this linear algebra result that means if we take do means annihilator twice, then we get the original space. So that fact we used here, where we use that this fact here, this this kernel, yes, this kernel of this more this k linear surjective homomorphism, this k n dual to t star, where t is that means zero set of those linear polynomials. So that this is a surjective map and its kernel is this t annihilator of t, and t is itself is an annihilator of this ip lin. So if we take this annihilator twice, then we will get the means original space. So so the kernel of this row, this map, this is actually ip lin. Here we use this fact that this is a linear algebra result here, taking annihilator taking double annihilator, say taking double annihilator gives back the original vector space, original linear space. So this was the idea. So the proof is a little tricky. We had to use this some linear algebra results and some observations, and yeah, I also gave you some checking to do. Yeah. Okay. Anyway, let me stop here. Thank you.